Great. Hello, everyone. We're going to get started. So I'm Mike Levy. This is Leadership Today. We're the software engineering co-chairs. This is the agenda. It's also available online. We only gave ourselves 10 minutes for this welcome, so we'll probably be running 5 minutes late, starting with the first talk, but we'll take that out of the discussion. We do want to highlight two things. One, Chris is here, so he'll be in person, not remote. And then the discussion is going to involve everybody. I'm going to be watching. I'm going to know if you don't say anything in the discussion. I'm going to hold it against you. So just a few other highlights. So Eric had a poster yesterday. I didn't realize the posters were all going to be taken down at the end of the session, but I'm sure he's carrying it around with him everywhere he goes. It's his little challenge token. Cheryl Craig is giving a talk in the 30th anniversary celebration later today. And then tomorrow at the end of the event, we're going to have a happy hour at the Rayback. We know there are a lot of people online that are local, but weren't allowed to pay a registration fee to come in person. So we're hoping we can actually get together in person. And so this is just like a mile east on Valmont.
Okay. Well, just to provide a few updates on what's going on in NOAA, and this is like a really big title, right? NOAA updates. We could talk about lots of things, but just in terms of Earth system modeling, we have been working over the last few years in the development of the UFS, the Unified Forecast System, which has a lot of touch points with the CESM, especially in terms of infrastructure. So UFS is a community model. It is supported by EPIC, the Earth Prediction Innovation Center, which is entity, it's a contractor funded by NOAA. And this unified forecast system can be used for both coupled global scale simulations as well as a limited area regional model. UFS currently only has one dynamical core for the atmosphere, which is the FE3 dynamical core. And as far as physics, it uses the CCPP, Common Community Physics Package, for interface with the dynamical core. And we're also bringing several simple atmospheric composition aspects like smoke, wildfire smoke, and dust into the CCPP for that connection. As far as marine components, UFS is using the MOM6, SCI6, and WaveWatch 3, so lots of overlap with what the CSM is using. Land surface models, we use the RUC for the short weather applications, but then the NOAA, NOMP, and more recently, we also brought the GFGL LM4 for those longer timescale integrations of the UFS. We're also connecting a number of fire and atmospheric composition packages, such as the community fire behavior model developed in great part here at NCAR REL, but also GoCart from NASA and CMAC from EPA. So then we use this set of infrastructure building blocks to create a number of applications, which are the apps, such as short-range weather for scales of hours to a few days. We have a hurricane application, medium-range weather out to a couple weeks, subseasonal, seasonal, air quality, coastal, etc. These applications are all in different levels of research and deployment into operations. So some are already operational at NOAA and SEP. So in addition to these component models, there are a number of infrastructure touch points with CESM and with NCAR and with CEMA, such as the CMAPS mediator, the CDEPS data models, ESMF for coupling, FMS infrastructure, that's part of some of your component models. And also, we are exploring the inclusion of MPAS-A dynamical core. I'll talk more about that later in my talk, but we've been greatly inspired by the multi-die core infrastructure in the CSM to implement this. So just a few highlights of things that happened in the UFS in terms of deployment since the last workshop when I was here giving an update. The HAFS, which is our hurricane analysis and forecast system, with the new version is going to be implemented in operations now next month in July. And that's a regional configuration with moving nests that are tropical cyclone following. We have the RRFS on the right. That's the Rapid Refresh Forecast System version 1. That's going through last science tests for implementation in March of 2026. The figure there is the smoke prediction from these Canadian wildfires that happen and are happening since last week. Also on the lower left, we have the fact that we have incorporated a number of idealized capabilities that have been released with help from the community. I saw Christiane Jablonowski was here a second ago. She contributed a lot to this capability, and now there's a tropical cyclone idealized capability, so it's not just the operational part that's being developed. And on the lower right, we have the SFS, that's our seasonal forecast system, planned deployment 2028, also fully coupled out to 9-month forecasts. So if you would like to learn more about that, you can attend this workshop that has a very strange name. It's Unifying Innovations in Forecasting Capabilities workshop. It will happen here in this same room in September. It's free, and it's also available for remote participants. Will be in hybrid format. So thank you, and pass it back to Mike.
Cool. And so just a few CSM updates from the last year. We've made a handful of beta tags. We're actually calling the model CSM 3.0 now, so beta 1 came out right after the last workshop. We're up to beta 6. I think a year ago we told you that 3.0 is going to be a development release and that 3.1 would be the production release, and that turned out to not be true. So we're planning 3.0 as a production release. Don't really have a timeline. It'll happen eventually. So I asked for updates from the various component models, and so this is a slide from Kate on the addition of a data glacier model. It's a simple way to describe impacts of glaciers on climate. It's similar to the CESM no evolve, but it's better in a few ways. So it's a smaller code base, it runs faster, it can handle surface mass balance and fluxes in a way that's good for CLM. It's very similar to active CESM in what it passes through the coupler, so you don't need to consider it as a special case. It includes this surface mass balance hole filling parallel algorithm, which Kate can tell you all about, and I know nothing about. It's got land ice fluxes that are now, I guess this is a change in the whole CSM model, is that land ice fluxes are now rerouted through the runoff model instead of going directly to the ocean, which just means fewer runoff maps that need to get made as you introduce new grids into the model. Sam put a lot of work into the CTSM documentation, so there's like this whole new system that really simplifies how the documentation is created and how it's pushed to the web. And it includes a whole bunch of new features. It's part of the GitHub workflow. It automatically updates when you change the source code, and you can build the documentation previewed on your local machine. You don't need access to the supercomputer. So when you're home and bored and don't know what to do, you can update the CTSM documentation. A couple of other quick updates. CAM released CAM 7 and dropped the Olarian die core and also the SP CAM configuration. MOM 6 now has support for the BGC tracers in Marble. It's got improved ocean and wave interactions, and there's a new sub-mesoscale parameterization. Cupid is the CSM unified post-processing and diagnostics package. Is now part of the CSM workflow, so you can run notebooks right off the bat. I said it was introduced in beta 6. It might have actually come in beta 5. We're really focused on helping Cecile Hene in running the CSM3 development runs and producing diagnostics off of those. But I think once we get past that, it'll be useful to the wider community as well. I thought I added a slide. Alper and Allison asked me to advertise a workshop. Do you want to just shout out the name and I'll repeat it? It's the correctness and... So the second workshop on correctness and reproducibility in Earth system models, and I reproduced that title, so I am qualified to go. Awesome. So with that, we'll jump right into the first talk, which is Anne. I'll let you know.
Get into the next.
If you just wait, it'll.
Okay. All right. So, well, my name is Anne. Thanks for the. I'm a little bit shorter. My name is Anne. Thanks for the organizer for accepting ESM team's proposal to come here to update the ESM recent progress and also future roadmap. So hopefully in the next 10 minutes or so, I can kind of remind people a brief overview of ESMF and then talk about some selected change from the last year or so related to CSM, this group, and also possibly talk about future short-term and long-term roadmap. So for those who don't know, ESMF is basically stands for the Earth System Modeling Framework. It is a high-performance parallel software infrastructure using coupled Earth science applications. To promote, let me see if I can use this. Cool. To promote interoperability and usability, ESMF provide the standard model component utilities and also standard definition of state object. And to enable easy coupling of the models, ESM also provides several methods for regridding. And lastly, ESM also focuses on performance by enabling parallel computing and also resource management. So because of that, a lot of applications uses ESMF as their underlying software. You can see this should look very familiar, CSM. That's why one recent work here. And also UFS, which kind of referenced by Lydia earlier. And there's also other international applications such as NorESM from Norway. And I think the Australia Access is just coming on board. So there are many applications that uses ESMF as an underlying software. So in addition to the ESMF component features, ESM package also provides NUOPSI, which is an optional interface layer that basically make the interoperability and usability simpler. And because of that, a lot of applications elect to also use NUOPSI into their application layer. For example, the CSM. And hopefully this looks familiar. This is the architecture of CSM with a lot of models linked together. Here I highlight with purple background to indicate this is where the ESMF is being used. It's kind of hidden in the background, so I just want to kind of highlight that a lot of the interface layer for each models to wrap around it, the CMAPs and also the CDEP's underlying data models, all supported by ESMF. And because, like every other software development team, ESMF is being used by a lot of applications, the team strive to make improvements and updates to the software. So I would like to take this opportunity to talk about some of the relevant changes to this group from the last year or so. Since I was here last time, I think March 2024. So because of that, let's jump into a selected list of change. So in May of 2024, we push out a patch, 8.6.1, and there are two noticeable changes that may be relevant to this group. One is the improvement of ESMF config class, which make it more robust. And this may be relevant to CSM because you guys are using NUOPSI.run config in your system. And then, sorry, Eric, back. I see Eric right here. So we also accept direct request. Eric was able to caught that bug that helped us update the ESMF mesh, unstructured mesh file so that we can dynamically connect the indexing to an attribute of a variable. So thank you, Eric. Call out. And then in October 2024, we push out 8.7.0. In there, we add a new repeat capability in the ESMF clock, which may be useful in spinning up the model. This is a feature that was actually requested by NASA. They're looping the historical data so that they can spin up the model until it gets into an equilibrium state, and then we can progress with simulation. I kind of call this out because it could provide an alternative for CSM's current mechanism for spinning up and handling of data streams. To use this capability, the user will set a repeat duration as seen here. And then so when the current time, which is represented by this green line, reaches start time plus repeat duration, you will then go back to start time. And then it keep looping until the user stops the looping so that you can proceed with the model. As you can see, go all the way to them. I hope there's some Marvel fans that recognize as Dr. Stranger. In addition to this capability, 8.7 also makes some improvement in the performance optimization. So for example, we have the reduced and regrid raw handle calculation was improved. And for some cases, for NASA, this improvement decreases the raw handle calculation time by a factor of 20. We also try to reduce the memory requirement for application that have a large number of arrays or fields and that runs on large number of pets. And then the third sort of notable change in 8.7 is basically in the new object connection option, we now support a remap method, regrid method, the second order conservatives, and extrapolation method nearest destination, I believe. And I want to use this opportunity to sort of call out that actually ESMF, one of the advantage of using ESMF is that we provide many different type of remapping method. Here's a table summarizing various methods from bilinear to nearest D to S, according to summarize its pros and cons and the typical uses. I'm not going to go through all the text here, but I just want to kind of hammer the fact that, depending on what you want to use, you may want to choose bilinear, which provides a smooth interpolation, versus a nearest source to D, which may provide which copy existing values, so you'll be probably better used for land type of application. So we think that, for me, I'm kind of new to this whole climate science era. So this table is very useful for me. So I'm hoping that this table will be also useful for new scientists, engineers, was they were trying to connecting models together so that they have the right interpolation method for the methods. So we hope to kind of include this table in the new release documentation. Okay, coming back to regular programming. So after 8.7.0 is released, we push out 8.8 in early this year, January 2025. There are two big changes in 8.8. Basically, the first one is performance optimization. This is a deeper improvements such that we basically remodel the state reconcile function. Thanks to Brian Dobbins' team, we're able to kind of do some characterization with this improvement. As you can see in the graph here, we were running CSM3 at 7.5 kilometer global at the 65,000 MPI ranks. And then the blue is the older version, 8.7. The red is the newer version, 8.8. The y-axis is basically the amount of time that's needed for initialization of the model. You can see that with the new version improvement, we have about 50%, or less than 50% improvement right here. Okay. Another way to also characterize this improvement is, again, with Brian's help. We're able to run with two different configurations that look at how when the components are spread, distributed across across processor. So on the left picture here is basically the configuration where two components were distributed 75% split throughout different processors. And you can see blue is the old version and the red is the new version, you can see here. As the MPI rank increases, the initialization time for both curve will increase, but fortunately for the new version is increasing at a slower rate, which is great because that means that it doesn't take too much time to kind of to do the simulation. Another notable thing to call is that at 65,000-ish MPI rank, basically the old version will basically crash, and that's why this blue line stopped right there. So with the new version, basically we're able to scale better as the number of MPI increases. The right side graph is basically different configuration where we have a total overlap of 4 components, and you can see that there's a blue line that's just increased quadratically and also crashes around 65,000 MPI. But with the red, which is a new version, which you barely see on the x-axis here, is really right there. It's barely increasing. So to us, it's a huge improvement, at least for this case. Yeah. In addition to the performance optimization, another notable change in 8.8 is the second order remapping of the exchange grid accuracy improvement. And I think this is relevant to CSM because X-grid is now the default for atmosphere ocean flux calculation CSM. So because exchange grid is basically the union of all vertices of the two parent grids, as you see here, atmosphere, ocean in red, and then here's the exchange rate. The benefit to the CSM is that calculations are always done at the highest resolution, and the user is not forced to choose between which grid to compute on. So you're trying to kind of preserve as much as you can. Okay, so because of these two changes, actually the ESM team will recommend that if you have an older ESMF running, it will be best if you can kind of upgrade to 8.8.0. Mainly, most importantly, is because of the performance optimization that we're able to improve. Okay. The team is currently now working on the next release, which is 8.9. We're targeting early July, and there are some potential relevant changes to CSM. So you can see the nearest neighbor reproducibility fix that's called by Sam Robbins. Hopefully we'll fix that, as that means that the the calculation result will not change even when the number process changes. There are some new ESMF runtime debugging feature that we would like to push out. So hopefully that will be relevant for scientists, engineers alike to be able to help troubleshoot some of the issues that they may find. We would like to broaden the complexity of meshes handled by ESM gridding. There are also some requests of ESM Pi feature improvement. This is a Python interface for the ESMF. And this was, I think, requested by NASA, but once we spin this up, it could be relevant to the CSM group as well. And lastly, we want to promote collaborators, and therefore there's some trouble with building ESM documentation from forks, and then we hope that with this change we're able to enable some of the collaborators to be able to build the documentation as well. Okay. So those are short-term sort of role plan. The new, the longer-term role plan, we have a list of things to do. Just to remind people that ESM is being used by a lot of applications, therefore ESM team get a lot of requests and then through the various different channels. And therefore, this is the short list of relevant potential future improvement that for CSM group. So there's additional efficiency improvement. Earlier I had talked about performance optimization. We show some improvement in the initialization time, but we'd like to make more improvement there. There's other direct requests directly from CSMs, as you can see some of the pictures there. There's a signal alarm restart. There's ability to write mesh and convert various grid formats to ESM mesh. Reading shape file into mesh, regridding tool improvements, attaching metadata to ESM object and exchanging metadata through NeoPSI connector. This is a feature that was sort of hidden from other bigger features. So in order for other things to work out, this is actually a stepping stone that we need to get to that. There's multi-language support. Increasingly, people are starting to use different platforms, Julia, C, Fortran. So then this hopefully the ESMF will be able to get multi-language support in there. Merging, field merging, smoothing, blending, and other things that are on our list that we're trying to sort out and prioritize. And therefore, the ESM team is actually planning for a change review board this summer to help prioritize these features so that we can plan out for the next few years. The ESM team, unfortunately, is made up of a small group of people, as you see here. Most of them are here to support me in case people give me very difficult technical questions, which I have no way of how to answer. Therefore, they're right here, stand by. But this team is always eager to answer community questions. We basically people contact us through emails or the GitHub discussion board. But at the same time, notice that there's only 5 of us, and then with me as not really truly an engineer, I don't really contribute to the code. But our time is kind of constrained. So if you send us an email, we don't get back to you immediately, please do not despair. We'll get to you. The team is primarily housed within UNCAR CGD lab at Boulder, and then Gerhard is basically part of the Navy Research Lab located in California. Okay, thank you. Any questions? Good. All right.
So if there are questions, there's a microphone in the middle aisle. Oh, I think Leisha's got one, yeah.
You mentioned lots of performance speed ups and, had some plots there about now from the point of view of the user, what kind of simulations can we execute now that we couldn't execute before until you develop this capability? I know there's a lot of interest in high resolution, global atmosphere, ocean simulations.
That thing. Right now, I know there's some ESM people here can help me, but right now on a high level is the current performance improvement is mostly concentrated on the initialization of the models. And there are other improvement that's needed, which we're planning. I kind of show there that there's a regret store and whatnot need to be factored in. So we're hoping that we'll be able to get to that with funding. So, but thank you for pointing that out. ESMF has been 20 years in the making. We did a lot of sort of trying to kind of help with the interoperability and the reusability. So we had kind of addressed that. So now we want to focus on the high performance because the community needs that. And so we'd love to get some sort of use case from this group, and that way we can kind of be able to design our solution better. Okay? And then the way to reach us is, again, the email there, and also our GitHub discussion board. That's a new sort of feature we enable, and that's a little bit facilitate a bit better sort of community discussion. Thanks, Lija.
our next speaker. So.
All right. Is there like a pointer here? Is there like this little one? Point here. All right. All right. So, hi again. This talk is on the progress of expanding the UFS to multiple dynamical cores. This work is in large part funded through the Developmental Testbed Center, DTC, and Dustin Swales from NOAA. GSL is a technical lead. But we also have contributions from other players from NOAA GSL. So I already gave an introduction to the UFS before. So UFS is a community model that's used for research, but it's also the code base from which NOAA draws its operational implementation. On the left hand here, we have a number of operational models that NOAA runs every day in its operational suite, and it's too many, and it's multiple DI cores, multiple code bases, the physics all over the place, multiple workflows. So the idea of the UFS is to work not with NOAA, with the private sector and academia, to simplify this with a number of building blocks from which certain UFS applications can be constructed. So this is, let's say, a work in progress with already some success stories. So one of these revamped models that we have been working on is called the Rapid Refresh Forecast System. And the idea of the RFS is that it would subsume several others existing production models at NOAA and create like a more simplified, streamlined way of getting products to the end users. So RFS version 1 has been developed over the last couple of years using the FV3 dynamical core as a limited area model. It's hourly updating, meaning hourly doing data simulation and launching a new forecast, uses a 3-kilometer grid spacing over North America. That's this red domain here. 65 vertical levels, uses hybrid 3D ensemble variational data simulation, and also includes the smoke and dust that I showed in my initial intro slide there. So the idea is that this would subsume the HER, Rapid Refresh Forecast System, domains that run in operations, which are listed in blue. Okay, and all that was going very well. We put the model together. The model makes forecasts, but when we started testing this model in the springtime, there was some challenges noticed with the forecast of severe convection. So in this plot here, we have the HER version 4, which is the current operational model, our RFS version 1 in the middle, and the observations from MRMS in the right. And what we see is that the RFS was making very bulky, broad storms that are unrealistic, and this really got the attention of the NOAA Storm Prediction Center forecasters, who said, well, this is not really how we want to go forward with prediction here. So, and also what we saw comparing the HER with the RFS had very high precipitation bias, especially for high precipitation thresholds. So based on all that, there were recommendations to use the MPAS dynamical core for future versions of RFS version 2. So we've been embarking on building and expanding the UFS to accommodate the MPAS dynamical core. So a little bit about the architecture of the UFS weather model. So the UFS weather model is coupled. So these two boxes here represent the atmosphere, and the other box represents all other potential components like ocean, etc. But for the RFS, it's atmosphere-only model. So ESMF NUOPSI is used as the coupler mediator between the atmosphere and the other components. Drilling down into the atmosphere, we show here the architecture of the two dynamical cores. So when we started, we only had the FV3, but now we have brought the MPAS as a submodule into the UFS weather model. And we had to do several generalizations because many things were very hardwired to only have one dynamical core. And then the CCPP physics, which is the library of physical parameterizations, is connected with the CCPP framework for auto-generation of caps, which then connect to this green line, which is like an atmospheric driver that calls the dynamics and the physics as the model integrates forward. In a more like top-down kind of architectural view, this is how the UFS weather model works today. So you have a NUOPSI cap on top of the atmospheric component. It calls the SMF forecast grid, which in itself invokes the FE3 ATM atmosphere driver, which then calls the dynamics and the physics. So we've basically duplicated this structure for now and created the equivalents for the MPAS. So the CCPP physics is the same. All the rest are kind of duplicates. And there will be opportunities to do more unification in the future, but for now it's pretty much like a duplicate driver and ESMF forecast grid component. So where we are with this development, I would say like we have a stub capability because we are now able to initialize and advance the MPAS dynamical core within the UFS weather model, and we can invoke the CCPP physics through the framework, but for now just calling a basic hello world, so we're not yet fully passing variables for actual physics. So a lot of thought, a lot of work has to happen in the physics dynamic coupling, which we're calling P2D here in a few of the slides. In the FE3 dynamical core, the time step starts with calling the dynamical core, and then calling the physics, and then proceeding from there. In the MPAS A, at least the way the MPAS dynamical core is used in the MPAS standalone model, the physics dynamics coupling is different. So the time step starts with calling all the physics except the microphysics, then calling the dynamics to apply those tendencies, but for the microphysics, you use the previous time step because you haven't called the microphysics yet, and then you call the microphysics. So due to this different order of physics dynamics coupling, the atmospheric driver has to be kind of rebuilt to accommodate the different orders of calling things. The other thing that is quite different in the physics dynamics coupling is that in the FE3-based model, when you call the physics, those are first called, various physical parameterizations will see the same state, create tendencies, update the state. After that, subsequent parameterizations will always update the state before the next parameterization are called. However, in the MPAS model, the physics dynamics coupling is different. All parameterizations see the same state, return tendencies, and then the state gets updated once. So in order to make the UFS do that, we had to change all CCPP parameterization so they have the ability to return tendencies and do not automatically update the state as some of them do. So now the ability to do time split is controlled by the host model. So the physics itself, the parameterizations, have the ability to all of them return tendencies, and if you want to update the state, you can have the host model control that via nameless variables. So when we do that, when we change from update the state to return tendency and then use the tendency to update the state, the results are slightly different. As Allison would know, now we have to figure out if this is right or wrong. So for now, we're not using a method as sophisticated as others here at NCAR, but what we're doing is just comparing those two ways. So update the state versus return tendencies and then update the state. And we see that in some test simulations, that's not introducing any biases, but when we compute, say, root mean square error of one forecast against the other, we see that the difference starts small but grow as expected. And those are comparable to types of differences that we see when we run the model in different compilers. So far, so good. No red flags with this update, but more tests will be needed. There's additional work that we will need to get this physics dynamics coupling to work. So there are differences several types of differences between how the MPAS dynamical core treats the physics when compared to the parameterizations in the CCPP, and those relate to the array layout, Ki versus Ik, to the vertical coordinate that's used, height versus pressure, to the vertical ordering, bottom up versus top down, and to the thermodynamics equations. All these conversions already exist in the MPAS A standalone. So what work that we're doing now is to extract some of these conversions from the MPAS standalone model and plopping them into the new UFS weather model. So in addition to what we're doing, we know that there is more work needed in terms of I/O. And MPAS has parallel I/O, but does not have asynchronous I/O, which we need for the UFS. So we're going to be working with partners to develop a ESMF right grid component, or to connect the one in the UFS to the MPAS. And also we would like to have more work done in the coupling, because even though we're focusing on the RRFS, which is atmosphere only, 3-kilometer short-range weather application, in the long term, we would like to have the ability to run MPAS in the UFS for fully coupled simulations for longer timescales. So meanwhile, while we're getting all this into the UFS, we're also going ahead and doing research with the MPAS A standalone model. So we have updated our physics for this model and have been doing many real-time research runs a day in GSL, sending our model to a number of testbed experiments like hazardous weather testbed, winter weather, hurricane forecast improvement project testbed, and atmospheric rivers testbed. And we are very happy with the results that we have been getting so far, including GSL MPAS taking first place here in the hazardous weather testbed subjective evaluation of high composite reflectivity. So meaning the model is working well for severe weather. This poses a big challenge in how we manage physics, because we're using the MPAS A model, which does not use the CCPP, but eventually we need to translate everything to the UFS weather model, which accesses the CCPP. So this is kind of complicated diagram, but just to say that what we're having to do to deal with this complexity is abstract many of the parameterizations to their own repositories so they can be brought into MPAS A. They're using managed externals to do that, but they can also come into the CCPP as submodules. So by having those standalone repositories as the code base for both CCPP and MPAS A, we hope that when it's time to transition this model from MPAS A to the UFS for operations, it will be relatively seamless. So takeaway messages is that I think we've made quite a bit of progress in terms of getting the MPAS dynamical core into the UFS, having this stub capability now in place. We have a lot of plans on the way forward, and we have secured partial funding. There's a lot of work coming up on physics to dynamics coupling, the I/O, and coupling to the other components. And meanwhile, we are on the MPAS A bandwagon here, and we are trying to put in place lots of strategies to avoid divergence and have our development be synergistic, whether we use MPAS A or the UFS. Time or? Hi.
Curious why you felt the need to reproduce the, call it unusual physics dynamics coupling time loop in MPAS in RFS.
Well, possibly because that model is working really well. So we've had a lot of experience working with WRF over the years, and it has performed very well for that type of severe weather applications. So that's why we are retaining it. But I think that by having this opportunity to have the physics return the tendencies, it now really opens the door to a lot of experimentation in terms of process split, time split, and how to dribble tendencies. And, you know, we're just opening the door for a lot of science.
Standalone in this version in NOAA.
That's like the reason for this diagram. So right now we don't use the physics that one would get when they just download MPass standalone. We have put our own physics that we lead the development for in GSL. You know, we have integrated that into the MPass. And we're using this strategy to also bring it into the CZPP.
Fine.
Jesse, you're up next.
Okay, cool. Hi, so my name is Jesse Nussbaumer. I'm a software engineer, as it says here at NCAR CGD in the AMP section, the Atmosphere Modeling Group. And I'm here to give an update on SEMA and the CCPP, or at least how we here at NCAR are using it. Before I get started, I want to give a shout out. A lot of people have been involved in this project. I want to really call out the core software engineering team I work with a lot. Two of them are on the line, I'm guessing, maybe not, is Haipeng Lin and Michael Waxmansky. I also want to call out two people who are here in the audience, Cheryl Craig and Courtney Peverly, so feel free to make direct eye contact with them later. And so yeah, and then Adam Harrington, who's also here, has been heavily involved in this work. Let's go. So real quick, I'm following the standard science talk outline. So we're going to do with pretty pictures first, then we're going to do important stuff, and then we'll end on pretty stuff so you can forget the important stuff. Okay, so yeah, real quick, if you don't know what SEMA is, it stands for the System for Integrated Modeling the Atmosphere. And the idea behind it is essentially, NCAR has a lot of different atmosphere models. They're all trying to cover different space and time scales. CAM is kind of the climate scale, and then WACM and WACM-X extend that into places like the ionosphere. And we have MPass and WRF, which is for the weather scales, and then it kind of goes farther down into smaller, process level scales. So the motivation behind CAM SEMA was essentially, well, we should create kind of one software framework or ecosystem that can kind of cover all of these different domains and allow for kind of cross-scale science collaborations. And CAM was chosen as a good base since they already had, WACM, WACM-X, CAM, and stuff, and MPass coupled in already. And this diagram shows that, we're going to cover all scales. I should emphasize that the current CAM SEMA goal is to just cover global processes. That does include weather timescales, but yeah, we're not, right, as of now, we're not going down into things like LES scales. So one of the motivations for this talk is, this is not my figure, and this is kind of old, and you can tell when it started, it was in the mid-2010s, and then they said, by the mid-2020s, we'll be done. And we not quite there yet. So what is the timeline? So I had a really hard time figuring out when SEMA, or was really called single track, started. I've kind of bounded it. So 4.5 billion years ago, the Earth system forms. And I'm pretty confident it didn't happen before that. Then by sometime before 2018, an actual document come out describing the single track. So it's between those two dates is when single track was created. So most of us didn't really start, a lot of the software engineers who are on SEMA now didn't really start until after 2018, I started in 2019. But I can say that in February 2021 is when the actual CAM SEMA repo came into existence. So I'd say that was the starting point of SEMA itself as an independent software project. So we plug along, but then we do get a setback. Basically in fall of 2023, we had several major science and software developers who were leading the SEMA leave and going to places like different countries. I remember the time thinking, what could happen in the United States that would make you want to leave here? Anyways, so in 2024, about a year after that, we kind of hit a milestone. We were able to successfully run an idealized physics scheme, a moist baroclinic wave, in the CAM-SEMA framework. This includes the CCBP with both the SE and then actually a little later the MPAS die cores. And so what's the current status? So right now, me and my team are working on bringing in, modifying CAM4, CAM7, and then M-Cubes, working on M-Cube physics to become CCPP compliant. And we'll describe CCPP a little bit later. But that basically allows it to work in CAM-SEMA. Also, ACOM team is bringing in new gas phase chemistry software, both specifically MICM and TUVX, into CAM-SEMA. And ultimately, our hope is to have a real CAM4 configuration running by the end of the fiscal year. Originally, we were also aiming to then have a real CAM7 simulation running shortly after that, but I was explicitly told that we cannot say what's going to happen in the next fiscal year with this project. So just pretend you didn't. Okay, but anyway, enough about the science. So this is a software engineering workshop, so let's talk about what software engineering things have we done. Because I think a lot of people assume that this CAM-SEMA project is just taking CAM and moving it around to CCBPIs and that's it. But we've actually put in a lot of effort to try to improve the software of SEMA relative to CAM. So one major thing we did is change the model configuration. So CAM uses Perl, about 8,000 lines of it, to do all of the model configuration. So all like, sanity checking, generating the name list, making sure your build system's ready to go, all of that. So we replaced all of that in SEMA with Python. We did that for several reasons. One is all of these things interact with SEAM, and SEAM is written in Python, and so the integration is much cleaner going from Python to Python than Python to Perl. We have much more thorough testing, which we'll get into later. Right? Python is pretty easy to write unit tests for, and so we've written a bunch of unit tests to try to make sure that our configure system works as expected. But probably the biggest selling point is, I would argue it's more easily understood by users and developers. Particularly scientists, many scientists are now trained in Python. If we run the tutorial, most grad students even come up knowing Python. Very few scientists know Perl. And the other thing is, even if they did, there's a general argument that the syntax of Python is simpler to understand than Perl. If you don't believe me, this is the Perl, and this is Python code doing the exact same thing, which is creating a configure object. And so you can decide which syntax you prefer. All right. So another development we've done is documentation. We've been trying to start off from the beginning in SEMA with documentation, and we've tried to split up into 3 different categories. So the first one is pretty standard, the user's guide. SEMA will need a user's guide, and that's, again, just to describe how to use the model. That's probably not going to be much different than CAM. We'll probably end up stealing Sam Rabin's work and putting our name on it. That's pretty straightforward. One thing that we've added, which doesn't exist in CAM, is a developer's guide. And again, credit goes to Courtney and Michael. And most people have something like this, right? Like, how do I open a PR? How do I get that PR accepted? What's the testing workflow? But we also wanted to go beyond that. We kind of wanted to describe the design philosophy of certain things, like what's the workflow we're going through when we build the model, what's the when the model initializes, what's the steps that it's going through, and why is it going through those steps in that order. And the hope, and this already exists for SEMA, and we found that especially for software engineers, this helps a lot understanding the system. And then finally, scientific documentation. I would go ahead and argue that scientific documentation is maybe almost the most important documentation for these kind of scientific models. But they're really hard to write because ultimately software engineers and even technical writers can't write it. They need scientists' input. And for CAM, usually what this happens is right around a CSM release time, scientists go, oh, we should really write scientific documentation. And everyone goes, yeah, we agree. And then we don't do anything until the next CSM release. And so the hope is to kind of lower that barrier. We will try to write documentation as we're doing development. And this is actually, we're just copying things that like NOAA and stuff have already done, right? These tools already exist, things like Doxygen. Or this is an example of Ford, which is basically a Fortran specific version of Doxygen. And this, I should give credit to Quan-Chi Wang, who is a software engineer at M-Cubed, who's been working on this. And the idea being that as we write code and we add comments, if we can try to add scientific documentation, in this case it's converting from potential temperature to temperature, we kind of set up a baseline so then when the scientists do come in to like write the scientific documentation, they have something to start off with. And our hope is to expand this out, right? Right now it's just functions, eventually become full physics parameterizations, and then eventually up through dicores and whole model. And then, yeah, I'll go through this quickly. We're also trying really hard. We found this through CAM4. There's a lot of math that has no documentation at all. There's no citation, no provenance. And so we're trying really hard to track down where some of these equations came from. And ideally, and we try as hard as we can to get a DOI for everything. So, then for testing, we really, in CAM basically has no unit tests, and CAM seems to have tried really hard to write unit tests that are then run automatically in GitHub whenever you open a PR. Right now we have kind of 3 sets of tests. We have the Python unit test. Remember, the configure code is all written in Python, and that's pretty robust. We have over like 130 tests, something like that. We also have Pylint code that automatically runs on any Python code that's been modified. And then we have Fortran unit tests. And this right now we only have a handful, but since we set up the system, basically every new PR has kind of added 1 or 2 more Fortran unit tests. So we're slowly building that out. And I should emphasize this is on top of the regression tests. Just like CAM, we have a bunch of full system integration tests on derecho, which we've also tried to optimize because in SEMA you can run with just a single physics scheme. So we're also running regression tests with just single physics schemes instead of the entire configuration. Okay, so then this next section, last section, I'm going to talk about the CCPP, which I would argue is an improvement over what we've had in CAM. Just in case, CCPP, the Common Community Physics Package, multi-agency effort designed to create portable and interoperable physics that we can try to share across different host models, different Earth system, climate, and weather models, and allow for scientific experimentation that otherwise wouldn't be possible. So what is this by SEMA? So here's an example of physics parameterization, Rayleigh friction. And on the left is what CAM was originally, and on the right is the CCPP's version. And the first thought people have when they see this is, oh, you made it worse. It looks so much more complicated in the CCPP's version. But I'd argue it's not, and it's not in 2 key ways. One is, while the calling structure is simpler, these data structures are CAM specific. So if you wanted to take this Rayleigh friction code and put it in any other model, you would either have to you'd have to replicate these structures or pull them out or find some way to translate from one to the other, which is a major kind of software engineering burden. These, on the other hand, are all primitive types, and they're all basically variables that every atmospheric model would have, right? Wind, change in wind, change in heating. And so that makes this physics scheme much more portable. The other thing that helps is it also arguably makes it readable. I can just look at this list and get a general sense of what the scheme is doing, right? It's taking in winds, it's calculating the friction, and then giving me the change in the wind and the change in the heating. Whereas this, I have to go farther down into the physics code itself to figure out what's going on. I do want to say that no way, though, does this mean that the framework is anti-object-oriented or anti-data structures. It just, we just want to be really careful. So if we do create an object or a data structure, we want to make sure that it's one that all host models can agree with and easily share. Real quick, I'm just going to hurry up. The other thing that really buys us, which is kind of the original selling point with the framework, was configurability. So what the CCPP provides is a sweet definition file. So essentially it's an XML file that just lists the order of the physics schemes. That makes it really easy to change or swap or anything like that. We ran into this problem in CAM. CAM has a big Fortran code, the phys package, which does all of this, and we learned the hard way that rearranging that can take months and months of effort. The other thing we've also bought, which isn't CCPP specific, but we've done in CAM, is you can now set the number of vertical levels at runtime and the number of advected tracers at runtime, which also means with the new gas phase stuff, you can set the chemistry scheme at runtime. Okay, so that's it. So here is that animation. This is provided by Adam Harrington, and this is the moist baroclinic wave to prove that I wasn't lying. On the left is CAM SEMA, and on the right is CAM, and you can see that they're basically the same. Okay, cool. I've convinced you. Yeah, thanks everyone. Appreciate it.
Questions for Bessie?
I was wondering if you could talk a little bit about the Fortran unit tests you have on GitHub workflows and what sort of did you need to do anything special to get them to run on the GitHub runners?
And CMake, and we're just right now we're mostly testing. We have codes that are like pure functions that have no use statements, and so those you just can kind of create an easy CMake build and build with them. So those things we're testing now, and we're slowly expanding that out. Like recently, the PIO actually, for example, so we've created this new file IO interface for these physics schemes, and we're using PIO, and PIO provides kind of like its already built environment, so that's also, we can just link to that really easily with CMake. So that's our current strategy. I think as things get more complicated, we might see about bringing in Seam or something. I don't know if that helps, yeah. Yeah, whoever?
Wondering about like high resolution scales like LES. You mentioned some things were dropped, and so what's the plan for that?
Yeah, I don't know if we have a plan. So I've been told, yeah. I mean, yeah. All I can say is right now, I got an email explicitly saying that right now we're only targeting CAM4 and SEMA, and we cannot say what kind of happen next because of the funding uncertainty. Again, originally my understanding was the plan was to try to allow for regional configurations and smaller scale. And some we need, like the single column model, CAM single column model. There's a CCPP single column model. But I don't know what the priority is yet. I don't think anyone knows yet.
I mean, is there a long-term plan for how regional configurations fit into SEMA?
So yeah, again, yeah, the focus is, if I had to take a wild guess, my guess would be that if they decide to go forward with that, I know like MPass, for example, now has a regional configuration, so we would probably like go through MPass, have that regional configuration, and then implement the physics, however that might be. That'd be my guess is how we do it. Yeah.
Thanks, Jesse.
Thanks. Cool. Thanks.
Okay, cool. Yeah, awesome. Okay, cool. Hello. There we go. How do we help scientists embrace their inner research software engineer, RSE? So my name is Eric Kluzik, and I work in the land model, and I have a great team that works with CTSM. So let's see, to advance, I push the button. Okay, so this is, I don't have a cool outline, and I don't have an animation like Jesse. We should all be more like Jesse. But what I do have is, here's kind of the problem I've been observing, it's been decades really, is that scientists contribute a ton of code. Oh, does the little fancy thing, I can point at the small screen. So there's scientists that contribute a ton of code, and of course, the model is science, and so that's what we need. And we as software engineers contribute some code, and sometimes we don't interact enough. And sometimes scientists, scientists are untrained in RSE practices, and they need to concentrate on their science, and they don't have time to work on RSE type of things. So how can we increase the collaboration between RSEs and code contributors, the scientists? And this is some things we've been doing about adding lines of collaboration. The goal is to encourage better software development practices from everyone. And, to get this kind of thing where we're working together, there's more collaboration both sides, and we're teaching some RSE things that are going to help the scientists do their work as well as help us. So, so why should CSM scientists care about the code? So the thing is that CSM is science, but it's expressed in software. So if you touch any CSM code, you are an ERSE. So, and you embrace that. That's a good thing. And bad software practices also kill our science. Clean software and software development practices make CSM science easier, more flexible, robust, verifiable, correct, reproducible, all those good things which are important for science. And so how do we encourage scientists to improve their coding practices? And these are some ideas that I have. Help them to see that poor code impacts the science. Oh, where's the button? There it goes. When problems come up, examine the causes and how to prevent it. Point out missing practices that could have helped when you see that. Point out the cost of having poor practices and how that's greater than the cost of having good practices. So here's an example of this, and I'll talk about this a little bit later. But we have a scientist, Adriana Foster, who also lovingly embraces her research software engineer and did some work where she looked at a subroutine and noticed a weird behavior that is going to have a science impact. And so, you know, doing kind of RSE unit testing kind of thing helped improve the science. So, so what does work? I think I got this in the wrong order. Okay, what does work? Demonstrate costs, demonstrate practices, educate on practices, and work with people with the highest interest in RSE work. How do we encourage scientists to improve coding practices? I'm kind of repeating myself, aren't I? But RSE team, so one thing we need is that we as the RSE team need to be actively doing and experts in these practices. We need to have education resources available, tutorials, documentation, etc. I'm also convinced that we need to use metaphor and non-technical terms to communicate better. Encourage people that try and provide them help. And education on those practices need to continue to be done. You're never done at doing that. We probably only can introduce one practice at a time and make most important things easy. And these things in the red are the things that are realized we need to be doing and we're not actually doing right now. So these are all the things that I came up with that I noticed do not work in a community model, in, you know, like demanding that scientists do whatever, shaming, claiming, all kinds of things just doesn't work. So, but let me get back to the point of what makes doing RSE type tasks hard, and this is really doing any kind of coding in CESM. And, you know, what can we learn from the software engineering industry? So debugging is the most expensive thing we do. It's inherently intractable. It's not possible to estimate. The further along in the development, the more expensive it is. And if you have brittle, poorly designed, poorly tested code, it keeps you constantly debugging. So it keeps you in, I call this debugging hell, and none of us want to live in debugging hell. Although some of us have to live there, but let's try to avoid that as much as we can. So we looked at this with our team. What are the problems debugging poor code? And it looks like half of my time is spent in debugging hell. In our team, it was kind of, they thought it was around 20%. And so, you know, one thing you can do with that is you can identify problems with the code and refactor to improve the code that's problematic. For that's commonly changed, problematic enough, that sort of thing. And so what practices does the software engineering industry show that helps? And there's three things I'm going to give here. And one is requirements. Reduce the set of things that you need to do to as small as possible, not too much nor too little. And spend effort into the design of the code itself. Again, brittle code, poorly designed code is hard to work with. Add automated testing while you develop, test-driven development. So, and the thing is untested code is broken or it's going to get broken. So don't add untested code and continue to run your test suites. Because it can get broken later. And so these are some list of RSE suggestions that I came up with, and I presented it to the CTSM scientist. And the thing is, all of these things are great, but it's too much. I realized it's too much, and so I kind of need to, present one thing at a time. So what are some things we're trying? So we're trying a thing called parallel work sessions in CTSM, which hopefully will mix research software engineers and scientists, and there's also hackathons that happen, which are great in getting that collaboration going. We made it easier for scientists to add stuff to CTSM because we have this bit-for-bit development branch, and so more people can contribute to the code easily. We're giving scientists a stable development version with our minor version updates. And with that, we realize we're freer to bring in small updates on main dev, which can include hot fixes. We've been doing Python unit testing, and that's like a standard now, and that's really great. And I think Jesse said this, that Python is really slick with their unit testing. We're educating more people on our PF unit-based Fortran unit testing. And there's scientists using Fortran functional testing, which I'll talk about a little bit more later. And then I have a survey, and I'd like everybody to take my survey, everybody here, as well as everybody that you see at this conference. So PF unit testing for Fortran code. Again, we've had it in place for a long time. I'm convinced that it's something we need to do more of. I was able to teach Keith Olson, who's a scientist, to do this, and he was able to figure it out, and he sees the point, and he'll do it again. So I'm hoping I can teach more scientists about how to do this. So functional unit testing, this is something that Adriana Foster has developed, which is kind of a unit testing framework to build drivers for science subroutines. It includes NetCDF input and output and Python plotting. And she's been teaching this methodology to some other people as well. And it includes people like Linnea. And she's using this for faster development of a machine learning parameterization. You don't have to go in the job queues, you run reactively, the builds and the runs faster, input and output is simpler, it's just accelerating what she can do. So that's awesome. And then again, here's the example of the behavior, she's looking at behavior of passing it a science subroutine, input, and then plotting plotting the results and comparing it for different things. And sometimes it points out some bad behavior, which is great. So we're hoping to do more of that. And again, here's my survey. I'd like everyone to take it. And questions. So, and I can't just have you ask me questions, but I have questions for you, because I'm still wondering, how do we encourage scientists working on the code to improve their development practices, and if we're working on that, how do we measure success? So, love to hear answers if we have them, and love to hear questions. Yes. Questions or answers? Yes. Okay. Yeah.
For many years, and I have found that the idea, convincing people that the cost of the practices is smaller than the cost of not doing the practices, it proves to be a very, very hard sell. And, you know, the theory is that by doing these practices, eventually you just demonstrate that that's the case. But I've found that even management won't back you up when it comes down to a trade-off between, do we meet this deadline by not following the practices and deliver this product that we promised by this date? Or, you know, do we do that, or do we violate the practices? And I'll tell you, meeting that deadline wins every time, hands down.
Yeah, yeah. Yeah, I think one of the things I'm trying to do is that when we have because there's the debugging hell thing I was talking about, and the thing is that, you know, throws a wrench in everything, and it throws a wrench in deadlines and everything else. And so when that comes up, I try to say, you know, if we had done this practice, we'd have been less likely to run into this problem, or it would have been a lot simpler. You know, so some work that I've done that, you know, takes a month, you know, could have taken, you know, a week at most if we had better testing in place, for example. So I've been trying to do that kind of thing. So, yeah, but yeah, I mean, that's a good point. Yeah.
Sell it to management is when deadlines get missed because bad practices led to a delay, which has happened.
Cool. Thank you.
Okay. So we have one more in-person talk, and that's Chris Harrop, and then we'll have an online talk before the discussion.
Okay, that's interesting. How do we get... Oh, all right, good. So I'm going to talk to you a little bit about a federated workflow system that we're developing called CHILTPEN. And before I get started, I just want to make sure to acknowledge our funding from the SENA program at NOAA and our collaborators at the University of Chicago and Parallel Works. And I'm going to give you basically an introduction to federated workflows, a little preview of what CHILTPEN looks like currently, and just end with some challenges in future work. So I'd like to start with pointing out this paper by Peter Bauer, which you may or may not have seen. It came out at the very end of last year, talking about numerical weather prediction being at a crossroads. And the reason I bring this up is because it lays out in a perfect way the motivation for why we're doing this work on federated workflows. Essentially, he makes the argument that the way that we're doing development in NWP with the increasing requirements for increasing complexity of the modeling, there's no sustainable way for any single weather center to continue to provide the high performance computing power required to meet the needs of this. And he points out that, you know, one way out of this mess is the incorporation of machine learning and AI, which is much faster, so we can get some of that computing power back. But there's really, it's kind of an untenable situation. And so the idea is that going forward, in order to sustain this effort in continuing to improve weather forecasts and Earth system modeling with increasing fidelity and accuracy, we need to be able to actually create collaborations among multiple institutions that don't normally work together and harness computing power that's spread across different sites or and managed by different people. So if you're familiar with weather workflow management in general, one of the problems that you're likely familiar with is the large proliferation of workflow management systems. This is a common problem in workflow management, and it's also happening in our area of study as well. As you can see here, there's a number of workflow systems that have been developed specifically for numerical weather prediction and Earth system modeling. And the reason why I list this here is because I wanted to show why we're developing a new system. And the reason is that although all of these systems have comparable capabilities and they have various strengths and weaknesses, and some of them can harness computing power across different systems. They do this in a distributed fashion. It's not really a federated workflow system. So I'll get to that in just a second. So I found that there is often a lot of confusion about federated workflow systems. What does that actually mean? So I'm going to go into that a little bit here and sort of try to distinguish it from a distributed workflow system. So a federated workflow system is different. And the reason it's different is because it provides you a user who has some identity, and this user has logins on various systems. And these systems may be belong to different institutions that don't work together. It's different bureaus of the government, universities, and so on and so forth. But what you can do is you can have a so-called federated identity. So this person has their identity, and they want to access all of these systems. And to do that in a federated fashion, you have to have a identity management. So you have to be able to log into this, to something, to get, to verify your identity. And what happens is you get these tokens back. These tokens verify who you are and what you're allowed to do. And then when you want to access a system, you present these tokens, and you're either allowed to do the action that you wanted or you're denied. And by doing this, you're not relying on very fragile SSH tunnels, and you're not relying on a connection to be up. You can use these, you can take your identity, link it, your federated identity, link it to the identities of all the various systems you want to access, and and all of the access can be controlled and limited in scope, and you can reuse these credentials until they expire, and thereby you have sort of secure access across a whole set of autonomous resources that without having to maintain all these weird networking pipes and things like this. Okay, so what we need is a way to implement those clouds, a way to verify the IDs and handle all of the ID management. And the solution that we are using is Globus. So most of you are probably familiar with Globus as a way of moving data around between different systems. The Globus is actually a lot more, there's a lot more to Globus than that. So Globus, behind the main thing that allows you to do those data transfers is its ID management capabilities. This is actually a very complicated and difficult problem to solve, which is one reason why I didn't want to do it myself. So it's good that we have Globus to do that. But Globus also provides, in addition to its data transfer service, it provides a function as a service compute platform for serving compute. So what you can do is you can create compute endpoints on different systems with Globus. And then you can access these endpoints and run things at these endpoints by logging in with your federated identity and submitting functions, and they just run on resources that are acquired by Globus. So Chiltepin, the system that we're developing, uses Globus to handle that piece and makes life much easier. So the next thing that we need is a way to sort of handle all of the orchestration of all the different tasks and things. So Globus gives us the ID management and the creation of the endpoints and remote execution of functions. And then there's another system called Parcel, which is a Python-based workflow system that's integrated into Globus. Globus uses Parcel, which is the reason why we chose to work with Parcel here. So Parcel allows you to create a Python program that is itself a workflow. And with Parcel's Globus Compute executor, you can create a program that submits your functions to all of these remote locations, and it will orchestrate and keep track of everything, enforce all the dependencies for you. And so we are using the software development kit for part of Globus to log into that, and Parcel to manage the execution of the workflow. Okay. So the overall vision is that users will use Chiltepin to create Globus compute endpoints at whatever systems they want to use, whether they're on-prem HPCs or in the cloud, and then will, from wherever they sit, it could be on their laptop, it could be on another HPC system, it could be anywhere, run their Python program. The Python program automatically deploys these tasks to the compute endpoints where you have requested their execution to run, and orchestrates, it keeps track of all of the dependencies, tracks the failures, retries, all that sort of stuff. And you're able to take advantage of all of these different systems. So what you can do is you can now design workflows that span multiple systems, and you can deploy different parts of your workflow to different resources so that they run on the resources that are most effective. So for example, with machine learning coming into play, we now have physics-based models, we've got machine learning, there's a lot of different requirements. Some things may need just your typical CPU stuff, some parts might want a really high-powered GPU. All these things may be located in different places. There could be different disks, different storage, different file systems that need to be accessed in different places. The point is that you can deploy each part of your workflow to the system on which it's best suited. Okay, so I'm going to do something that you're never supposed to do in a talk, which is show some code and stuff. But just to give you kind of a little flavor of what this might look like. So Chiltepin gives you compute endpoint lifecycle management. So it's got a little command line interface where you can configure and start endpoints. So this is just kind of what it looks like. You create it, you just log into the system you want to make the endpoint on, you configure it, you start it, and then it gives you back this UUID, which you can then use to access it. So this sort of is meant to illustrate a little bit of what a workflow might actually look like in a Python program. On the left-hand side, there's a class, MPass, and there's these decorators, bash task and Python task. Those decorators automatically turn that function into a workflow task. And so if you call that function, it will automatically run that function on the resource that you specify. And the way that it does this is when it sends it to Globus Compute, Globus Compute will actually start up a job on that system, acquire the resources, and then run your task inside of that job. So on the right-hand side is just an illustration of how you might call these things. So when you call these, the functions return immediately, and they give you back a future, which represents the eventual result of that computation on that remote system. And then you can take that future and you can inject it into the parameter when you call the next function. So in this case, mpass init, I get that back right away. And then I call mpass forecast, which needs to run after mpass init has finished, but I give it the future as a parameter, which tells it that that's a dependency. And then that's how the workflow works. And then you can see I have these executors. I'm pointing on the screen here. It's kind of funny. How does that work? Okay, these executors that specify where that is supposed to run. At the moment, we're actually don't have anything to automatically have it go to, to choose a system that to run on, but eventually we would like to do that. All right. So a little bit about configuration. So you have to specify a configuration that describes the resources that you want to use. So in this case, we have a resource called Hercules, and you can give it a bunch of environment that tells, what basic environment setup that's required in order to use this resource, the endpoint ID, and then a little bit about how the resources are acquired. In this case, it's using Slurm and uses srun for its MPI launcher and some node configuration stuff. So that's normally you would have a number of these blocks for each resource, and you would just call them as needed. All right. So challenges in future work. So one of the challenges that we have is that we're not really used to workflows as Python programs. Usually we have a sort of a static description of a workflow in a YAML or an XML kind of format. And then there's another separate thing that's an engine that will read that in and then execute that. But in this case, what we have is we actually have a Python program that it itself is the workflow. And if the workflow fails and you rerun it, it will remember what it already did and it will skip over the things. But it's a little bit of a different paradigm. One of the things we need to do is to develop good monitoring tools. Parcel does have access to monitoring stuff, but we just haven't had a chance to develop really sophisticated tools for it yet to track, so that we can give users a good way of tracking the progress of the workflow. And similar with the built-in failure recovery that they have. And then the other thing is as the developer of Rakoto, one of the next things on the plate is to actually have this thing have support for legacy Rakoto workflows, so that it can actually read in a Rakoto XML and run it. And then, of course, continue to build this so that we have a sustainable workflow future, because without federated workflows, you're not going to be able to sustain the modeling efforts that you need to do.
In your example, and maybe it was just a contrived example, but you were doing the initialization on one machine and then the run on another. Is there a mechanism to get the data that you've produced in the initialization over to the other system?
There is. It's just there's actually a built-in workflow task for transferring data. That was kind of an example so that I could illustrate how you would do multiple systems, but it's an unrealistic example. So there is challenges in the data management, because the whole idea historically has been move the computation to where the data is, because moving the data is really expensive. But when sometimes you have to do both, and it's sort of sometimes it can't be avoided. But
can you say for the discussion now? Because we're behind. We'll have time in the last 20 minutes. And then is Phil online? Are we?
Yeah, can you hear me?
We can hear you. If you give us just a minute to get your talk on the screen.
Yeah.
Yeah, and we're ready for you to go.
Perfect. Yeah. Hey, everyone. I'm Philip. I'm one of the developers for the UX Array Python package. I work on the GeoCat team at NCAR. So today I'll be going over some recent updates and developments for UX Array. So for those of you that are not familiar of what is UX Array, we are an open source Python package that provides unstructured grid data analysis and visualization functionality for climate model outputs. So from CSM, MPAS, all of these different models. And our design is heavily inspired by X-Array. So we extend that package to provide a very similar workflow while providing unstructured grid-aware functionality. And we use packages from the scientific Python ecosystem, so notably Dask, Numba, and Datashader to accelerate our functions and to provide support for kilometer scale resolutions. So let me quickly go over what the UGrid conventions are, because this is what our package is based upon. So on your screen, I'm going to share just a couple grid formats. You may be able to recognize what they are, but for the sake of this presentation, it doesn't actually matter. What's important is that UX-Array can read in these formats, whether it's from MPAS, ESMF, ICON, ChemSC, all of these different model outputs. With UX-Array, we have a specific data ingestion step that can determine what grid format you're working with and encode them in the UGrid conventions, which this is a standard for representing unstructured grid variables, topology, connectivity information according to the CF conventions. So the main benefit to this is instead of needing to write separate analysis functions for different grid formats, it's a single tool that can be reproducible and operate on any supported grid format. And to go over some of the core classes that are part of our design, the first one is our grid class. And this is what we use to store our unstructured grid information. So this can be coordinates, connectivity, face areas, different descriptor variables that are used to represent the underlying topology of your grid. We then have a UX data array, which this represents a single data variable that resides on an unstructured grid, and it is linked to a UX grid. So the main difference compared to an X-array data array is that it's attached to that grid object, and you know what source grid you're working with throughout the life cycle of any operation that you're doing. And then similarly, a UX data set takes things a step further. It's just a collection of data arrays, all of which are assumed to reside on the same unstructured grid. And then very generally going over our overall design, I already covered our grid, data set, and data array classes, and you can see how everything flows right here. So we support those grid formats that are listed above. In addition to outputs from climate models, you can load in point data, you can have custom topology. We have a lot of flexibility in that regard. And then all of our plotting, regridding, computational operators, all are directly part of these custom classes that we've wrote. And the intention of this is to allow the user to transition their existing structured grid workflows to unstructured with minimal code changes. So let's look at a basic example. Here on the left, we just have 4 lines of X-array code. We're loading in a data set, opening it, and then plotting a data variable. Relatively straightforward. With UX-array, there's really just a couple changes here. We use the UX-array package instead of X-array. You need to specify your grid and data path because we need to be able to interpret what source grid your data is on, and then all the other syntax is identical. And these plots look different. I did some very basic regridding for the left one, so it's not a apples to apples comparison, but the one on the right is your original unstructured data. The one on the left is just some dummy data for the presentation. And let's go over our toolkit of functionality. So we have an extensive set of visualization functions, both vector and raster based ones, and there's a few examples here. And these are written around the HoloViews and Datashader packages. So it was our intention to allow the users to visualize the highest of resolution grids with without needing to worry about performance. And we are also currently working on some custom sampling techniques to enable native matplotlib workflows, which we know has been requested by the community. And let's look at some of these plots. So this was a 3.75 kilometer MPAS model run. And with by using data shader and hollow views, you can interactively zoom in to a region of interest. And if, for example, you're on a multi-core machine, it can dynamically in parallel re-rasterize as you zoom in, so that at a global scale, you may have your output image looks much coarser, but as you zoom in interactively, it dynamically re-renders your image. And this is all done automatically because of data shader. Let's go over some of our other functionality that we support. So I know in a few other talks there was some notes about regridding. We support a very basic set of pure Python implementations for, this is for subsetting, sorry. For subsetting, here we allow the user to quickly select and restrict the domain of their data using an Xarray-like interface. So couple snippets here. We support bounding circle, bounding box, and nearest neighbor based approaches for selecting your data. Let's see, we also support cross sections. So if you're working with trying to get all the data at a line of constant latitude, constant longitude, or between intervals of either, we also support that functionality. And everything is contained in a fluent interface. So the output of a cross section will be a brand new data array that is attached to a brand new grid that is restricted to whatever output variables you have. So we try to keep everything self-contained and working in a fluent manner, which again is consistent with how Xarray and other Python packages do things. And then I was a little ahead of myself on the previous slide. For remapping, we support a very basic set of remapping functionalities that are written in Python. So there's no need to depend on any larger external libraries. Because of that, our implementation is definitely limited compared to a lot of others, but for quick remapping, we support nearest neighbor, inverse distance weighted, and bilinear approaches, all directly contained within the package, and we do accelerate it using some data structures from SciPy and by using Numba wherever we can to get as much performance as we can. And then another summary of some of our other analysis operators. So we support zonal averaging, different types of unweighted and weighted averages, also topological aggregations and geometry routines. Again, as I've mentioned, we try to use Numba as much as we can for these core grid routines to squeeze out as much performance as we can in areas where Dask or other packages are don't really work with our existing workflows. And in addition to that, we are working with our SciParks intern more advanced vector calc. They're all in the works. And now let's take a step back and look at some more community resources and documentation. So as I mentioned, UXarray is completely open source. If you're interested in contributing or just taking a look at our code, there is a QR code for our public repository. And we also have an extensive documentation page, including a user guide, gallery, also contributors guide, and other pages. In addition to that, outside of our primary documentation, we have developed 2 cookbooks, which you may have seen these before if you've been following any of the UXarray development. We have both an unstructured grid visualization cookbook and a HealPix cookbook. So with the UXarray team, we're always looking for opportunities to enhance our community collaboration, and documentation in Project Pythia is one avenue that we use. And to summarize, so UXarray, it's a Python package that enables the analysis of unstructured grids from mostly climate model outputs and not just from formats that are produced by CESM. If you have MPAS models or some of the European models, we provide these lightweight ingestion layers where as long as we can load in your data and represent it in the UGrid conventions, you can take advantage of all of our analysis and visualization functionality. And much of it, we try to support kilometer scale grids and higher resolution models by leveraging packages like Numba and Dask. So I'll leave it for questions. I think we're right on time as well.
Thanks a lot for this. This is UXarray seems like a really great package, and appreciate your presentation on this. I'm curious, the capabilities for UX-Array to work with structured grids, and if I wanted to write like a generic, some generic Python code that could work on either structured or unstructured grids, would it make sense to just use UX-Array, or would there be friction in using UX-Array for structured grids compared with just using X-Array?
The main concern would be the way we represent structured grids. Because of the UGrid conventions, which our package is based on, we need to on the fly generate things such as your face to node connectivity, which isn't technically required if you're just doing a pure structured grid workflow. But for the sake of just having one grid that's structured, one grid that's unstructured, you should be able to use UX-Array. I would still suggest probably pure X-Array workflows would work better just for standard structured grids. And we have designed the package to be as close to X-Array as possible. So under the hood, a UX data array still inherits from X-Array. So they're both related, just UX-Array extends and builds upon what X-Array already provides. Thank you for the question.
Thanks again, and we'll switch to the discussion session. So to seed the discussion, we have a slide with like 5 possible questions you might already be thinking of, or you can use this time to ask questions of the speakers. So I think Ufuk, if you want to start by asking Chris your question, that would be.
About this new workflow tool, are you providing some way to reproduce your workflow? Are you storing some provenance information or metadata related with the workflow itself? Because some user can run the workflow in some machine with some compiler, but others will run another compiler and another machine. They will end up with different results maybe. So is there any way to replicate exactly the same workflow by sharing something? I don't know.
Yeah, I'm sorry. I can't believe I forgot to put provenance on the future work. But yeah, that's a very critical part of any workflow system is provenance, keeping track of how to do it again. Since it's a Python program, I'm wondering how that's going to work. I'll have to think about that.
So some potential questions to think about. Brian Dobbins had asked us to put this bullet about, like, how do we fund CSM software given proposed cuts to NSF and the NCAR base funds? I think tomorrow there's a cross-working group session on variable resolution and high resolution models, and that's going to be very science-focused. But I was kind of pushing for that event to happen because I think in this room we need to think about how the different components are going to interact with these new capabilities and trying to think of ways to be consistent across components instead of everybody doing it themselves in different ways, or whoever does it first gets to dictate how everybody else does it. Well, what can we do to strengthen collaborations between CSM and modeling groups or between NCAR and other institutions? This might not be a great discussion point, but something to think about and talk to Leisha and I about is for the next winter working group. Like, I thought the hackathon went well. We only had a day because we came up with the idea of doing a hackathon after we thought a day would be more than enough talks. So do we want a 2-day hackathon? Do we want some talks and some hacking time? Or anything else you want to talk about? So we have 15 more minutes. The microphone's open. I'm taking notes on who's talking.
I just mostly want to keep Mike happy. And I wanted to say thank you, Eric, for your talk. Like, that's really what I got up here, because I kept wanting to say, like, that was a really good talk and very thoughtful about how to do this. I work with a smaller set of scientists in the Land Ice group, but we're sort of trying to push them towards a lot of those things. And Bill Sachs told me about a testing script that you developed to run the CESM tests more simply, which was super helpful. So I'm just wondering, like, you know, if there's a way we could incorporate more of that sharing throughout the software engineering groups that we do so that other groups could learn, useful ways to improve RSE stuff in their groups. Also, I vote for 2 days of hackathon, and I don't know the answer to the other questions.
I wanted to ask, I think if you heard the Earthworks talk yesterday, they pointed out problems that we found in ESMF and PIO at very high processor counts where we frankly never test. And, you know, is there a way to reproduce those high processor count capabilities at, you know, small processor counts?
Hey, Brian, did you hear that? Yeah.
On testing is that when you write tests, they test exactly what you tell them to test. And these sorts of scales, because they require lots of resources, we can't do it via GitHub Actions. I'm not going to get a 2.4 billion cell mesh there. And this is more of a communication issue with, people here know I've bugged the director, and I'm like, you want to run these bigger things, we need bigger systems, and we need bigger allocations of time. So this is a communication issue. I don't see a technical way around this. Like, it's a question of, even with testing, like, do you write a test that takes 90% of your yearly allocation that you're gonna, that only occurs in one instance? So we do want more testing. We just have to be smart about the testing we do, and we have to realize you're never going to cover all the areas. You cover what is most important. So that's the important thing to me. That and communicating that, again, as we push into these regimes, we need more resources, people and systems. So yeah.
That reminds me, test coverage tools are really helpful in figuring out how good your testing is.
On this testing train, I just want to, and maybe we'll talk about it at the correctness workshop, so we don't have to bring it up here. But one thing I've struggled with is what makes a good test, because like we have tests for things like here's some function, and yeah, like I throw in numbers and it gives me a correct number out, but that feels like I'm just testing, yeah, the compiler successfully divides two numbers. It doesn't feel like a very meaningful test. And so I'm kind of curious what other folks do to, like, how do you decide this is a good test or a bad test? Think about it. I think.
Yeah, on that, I mean, it might not seem dramatic when you write tests and they all work. For me, I would take the rest of the day off. That would be amazing. But it more becomes useful when things start to break, right? And so, like, it's not really necessarily a compiler thing, but like adding in sort of edge cases, like what if you put all zeros into this? What if you put a negative number into this? Is the error handled correctly? And PF unit, unfortunately, can't really test like correct error handling at least, but yeah, it's sort of weird edge cases that are potentially the most useful.
Yeah, and that reminds me, testing the happy path is what most people usually do, but it's also really good to test the unhappy path. Test to make sure that when things go wrong, they're going wrong in the correct way, or that you're catching them correctly.
I'll also talk a little bit more about my philosophy on testing. We have to be careful because, again, getting to the resource issue, like there are lots of things we can test. Our code has so many degrees of freedom. And the question is, every time you write a test, you have to maintain that test now. And so the question is, if you're writing infrastructure code, like I think of it, if I'm a bank and I'm taking an account number, I want to check that no number was given to me. I want to check that I was given a string or a buffer overflow, stuff like that. If I'm writing something that takes in a 3D field, I can assume the people passing in it are sending in a 3D field and not a text string of, a quote from the Bible or something like that. You don't have to go to extremes, because then you have to maintain a lot of extra tests. So it's always a balance. So we think about it. And I think balance is maybe, I feel bad. Somebody was talking about before, management always has a different opinion. And I'm wearing both the software hat and the management hat and trying to balance things here. But I think it's important that we think about what we're trying to test, and we never, I don't know anybody in this room who has enough time to do all the things on their plate, and the same is true with testing. So think about what we really want to achieve, and write tests for that. If it's code that changes often, maybe we don't write tests for that much. We do statistical tests. This is one of the things we're moving to for our physics. If it's infrastructure code where you are adding numbers together and you want to sum, well, hey, that you can do pretty easily. But it's more about not testing everything, testing what is important to test and being smart about it. It's a really great conversation because I know there's a lot of different thoughts on testing and a lot of different ideas, and I'm by no means an expert, but again, that's the manager hat, being like, I'd love to have 418 tests for my Hello World program that takes a string, make sure it's not Unicode, make sure I can write to the file system, make sure, all these things, but that's not a good use of time. So it's a balance, yeah.
So getting back to what Kate was talking about, a couple of things there. So I like the idea of a 2-day hackathon, so that's my vote. And then Kate was talking about, getting us together and talking about how we're doing things, and I really love that idea. I don't know what that would look like necessarily. Maybe that's a hackathon, yeah. Maybe that is. Maybe that could be part of one of those days or something. Just how is everybody doing unit testing or whatever thing, and then we talk about how it's done and learn from each other. So maybe that's an idea. Let's see, and then testing. I think the code that gets changed is probably the code that needs to have the most testing on it, which I'm not sure if Brian was saying that or not quite, but he's got a good point that if it gets changed a lot, then you can't just check for an exact answer. But you can check for behavior. Is it monotone increasing, or whatever kind of characteristics it should maintain to have. Martin Clark had this thing about, he called them laugh tests, which were kind of basic things of making sure you're conserving mass, or simple kind of things, which I think we should do more of that as well. That would be more testing. The science behavior is what it should be. So that's another thing we can do. So anyway.
I'll maybe just add to and amplify some of these points. I think just building on Eric and Kate's discussion and some of the points here, I think you mentioned my consistency across components in the variable res and regional setup, and I think the more that we can work just in general to have I think uniformity across the different model components, rather than in ways that make sense, in places where we just have arbitrary differences. And I think the testing setups is a big one. Each component of CESM has slightly different workflows for how we do testing, and it's kind of arbitrary differences that don't, I think, have good reason. And I think we'd gain a lot from learning from each other, and also gain a lot in terms of just the ability to for software engineers to move more fluidly from one component to another if we develop more of that uniformity. And I think the more one way to get to that hackathons is a good idea, but also just if we had a little more culture of sitting down with each other and for an hour or two kind of pairing and working on some problem together and seeing, oh, you do it this way, oh, I wonder what's different from my workflow. And then just my thoughts on the testing piece. Yeah, I think just to add a little bit to what Brian said and amplify that. I think there's a good question that was posed to me at one point was when you're writing this test, are you actually worried that there's a chance that it's going to fail? Because sometimes it is easy to go off and just I want to test this case and this case and this case. But if you don't think that there's actually really a chance that your test is going to fail, that's the point at which you say, okay, maybe I've reached diminishing returns. But the other point on that is, for me anyway, a lot of the value in testing comes when you're doing it alongside the development, and it replaces the kind of manual testing you'd otherwise be doing, and that's where you really, where you really get the bang for the buck. And it's something I've struggled with that is, and so we're posing like a challenge rather than anything that I have a solution to is when we get science code. I think the value would have come in the testing if the scientist had written the tests along with doing that development, rather than presumably spending a lot of time manually testing and not having tests that are kind of developed as an artifact. But in my experience, like writing the unit tests can be a lot harder than actually writing the code. And so how do we actually get testing, good tests out of that from people that haven't spent years developing that kind of unit test writing, those unit test writing skills? I've struggled with that.
We're 3 minutes away from break, which is about, I don't know, many more minutes than I thought we get out of the discussion. So good job, everybody. Thank you. Jesse, did you want to say, were you about to get up? No, say it. Right. We'll have 2 more comments. We'll have you and then Kevin. Yeah.
Conversation, so I won't. But I guess first off, I also vote for a 2-day hackathon. So keep me on your good side when I ask for Cupid questions. But the other thing, which kind of going back to Eric's talk, and one thing I've kind of struggled with is we want scientists to know more software engineering, but at what point do you draw a line and say, like, no, this is knowledge that I just don't expect you to necessarily have. Like an example I can come up with is Git. So like obviously we want our scientists to know basic Git flows, like how to make a PR or whatever. But at some point, I don't want them to be doing like interactive rebasing and then coming to me because their ref log's messed up or whatever. So at what point do we say like no, this is our kind of like area of expertise and we don't expect you to. I don't have an answer to that, but if anyone has opinions, that would be great. Yeah, thanks.
Very quick plea or request that if you do go to the trouble of making a test, try to print out a number that is going wrong. Because if there's just a message that the subroutine failed, then somebody has to go in and add some code and run it again and figure out what number they're trying to fix. So whenever possible, print out a number.
Okay. We did it, team. We made it to break. Good job. So just a reminder, there is a happy hour at Rayback about 5:30 tomorrow. Hope to see you all there. Yeah, so there's something running here late, and so we can't do it tonight, but tomorrow. Cool. All right.